Imagine a celestial canvas, vast beyond comprehension, where planets once danced in vibrant hues only to fade to a monochromatic echo of their former selves. Consider Mars, the fourth world from our Sun, a ruddy jewel now, but a stark portrait of what might have been. By distance, yes, the fourth. By sheer physical presence, the seventh largest planet in our solar system. We have, over the last few decades, been granted an intimate perception of its unique, ancient landscape. Sense the grandeur of Olympus Mons, an extinct Martian volcano that dwarfs anything we experience on Earth. Not just the tallest mountain on the planet, but the greatest volcanic edifice in the entire solar system, a colossal shield spanning a staggering 600 kilometers at its base, its summit reaching an astonishing 26 kilometers above the surrounding plains. And then, contrast that with the epic geological scar that is Valles Marineris, an immense canyon system stretching some 4,000 kilometers across the Martian equator. A gargantuan rift that would cleave the entire continental United States from coast to coast. These are the titans of Mars, carved by forces beyond our terrestrial experience. Yet, beyond these monumental landforms, there are subtler phenomena that whisper tales of a more dynamic Martian past and present. We perceive, for instance, the occasional appearance of delicate white clouds, ethereal wisps that drift through the upper reaches of the Martian atmosphere. Now, as we understand, clouds do not simply materialize from nothing. For their formation, some fundamental particulate matter is required, something to facilitate the condensation of water vapor. For a considerable duration, even our most sophisticated climate models struggled to account for these high-altitude clouds. The atmospheric density on Mars is a mere fraction of Earth's, a delicate veil offering scant resistance, making the mechanics of condensation at such altitudes particularly puzzling. Then came the compelling discovery of what we term meteorite smoke. Picture countless microscopic specks of cosmic dust, the burnt residue of meteoroids that incinerate as they plunge through the tenuous Martian atmosphere. Each tiny particle, no larger than a micron, acts as a perfect nucleation site, a microscopic scaffold upon which water molecules suspended as vapor can cling, condense, and freeze. The process is remarkably analogous to the formation of noctilucent clouds in Earth's mesosphere, those shimmering electric blue phenomena that glow after sunset in our own polar regions, created by precisely this mechanism. This revelation, first uncovered in 2021, reshaped our understanding of atmospheric physics on Mars, suggesting that even the most fleeting celestial visitors leave their indelible mark, acting as the unexpected architects of Martian weather. This unexpected interplay between interplanetary debris and atmospheric dynamics forces us to rethink the very concept of a dead planet. Mars, it seems, retains a certain atmospheric artistry, albeit one dictated by the constant influx of dust from beyond. And this dust, this meteorite smoke, might just be the key to understanding a broader, more profound question about Mars's distant past. Could such fine particles also have played a role in sustaining an atmosphere capable of supporting liquid water for unexpectedly long periods? What other hidden connections might we yet uncover between a planet's atmospheric chemistry and its cosmic neighborhood? The more data we receive, the more complex and intriguing the narrative of Mars becomes. An interesting study, for instance, drew our attention to the analysis of some 200 ancient dry riverbeds across the Martian surface. These aren't merely shallow channels, they are relics of deep, wide rivers, a truly unexpected perception. What these tell us is that substantial liquid water flowed across Mars, not just fleetingly, but for an astonishingly prolonged epoch in its early history, possibly as far back as 4 billion years ago. Indeed, some estimates suggest that ancient Mars harbored oceans containing as much liquid as our own Arctic Ocean. To consider this makes the subsequent history of Mars, the inexplicable disappearance of that vast watery expanse, seem even more profoundly strange and, for a time, utterly inexplicable. Yet there are conflicting theories, a dynamic intellectual jostle for the truth of ancient Mars. Some planetary scientists contend that even in those ancient times, Mars was simply too cold and dry for the sustained existence of such expansive oceans. They propose a different narrative, one where water, though present, only achieved a liquid state intermittently. Imagine vast floods, unleashed perhaps by intense volcanic eruptions that temporarily warmed the surface and thickened the atmosphere, or by the colossal impacts of large asteroids plunging from the asteroid belt, momentarily melting extensive ice reserves. These would be short-lived episodes, cataclysmic interludes of warmth and flow, followed inevitably by a return to the prevailing deep freeze. The very landscape of Mars, etched with both grand river valleys and immense impact craters, seems to hint at both narratives, leaving us to wonder, did Mars experience a sustained clement epoch, or was its liquid past a series of violent, temporary thaws? And what of the frozen realm? Our instruments have unveiled another fascinating aspect of the Red Planet, its glaciers. Not static, unchanging masses, but dynamic systems, particularly around the polar regions and within certain craters which do not simply remain in one location. These Martian glaciers exhibit subtle yet perceptible movement, creeping down mountain slopes or flowing sluggishly across vast plains. They advance and retreat like colossal icy breaths, responding to the subtle shifts in Martian temperatures over extended periods. These majestic movements of ice do not occur without leaving an indelible trace upon the planet's surface. With every grind and shift, distinct landforms emerge, features we recognize from Earth's glaciated regions. We perceive the delicate curves of drumlins, those elongated, rounded hills often found in glacial terrains, sculpted by the overwhelming power of advancing ice sheets. We sense the subtle sinews of eskers, winding ridges of sediment deposited by subglacial meltwater channels. These landforms, alongside others, paint a very clear picture. At one time, these regions were dominated by active glaciers, shaping the very bedrock of Mars. Thanks to the extraordinary imaging capabilities of the Mars Reconnaissance Orbiter, or MRO, over a period spanning several Earth years, we've definitively established that these Martian glaciers do indeed move. They flow in the form of massive, viscous streams, albeit at speeds far slower than their terrestrial counterparts, perhaps ranging from 300 to 800 meters per year. This sluggish, inexorable flow continues to reshape the landscape, carving new features and subtly altering the planet's face across geological timescales. However, a particularly intriguing discovery emerged from the region known as Tempe Terra, located north of the Tharsis volcanic plateau. There, the MRO probe managed to identify geological features known as eskers. These are not merely ancient, inactive landforms, they are living testaments to the dynamic nature of Martian ice. Eskers appear as relatively low, yet remarkably long, sinuous hills, often resembling railway embankments snaking across the terrain. Unlike many other glacial landforms on Earth that are carved directly by the grinding movement of the ice itself, eskers are primarily formed by the powerful flows of meltwater beneath the glacier. This subglacial water under immense pressure carves narrow but extraordinarily long channels into the bedrock, sometimes tens of kilometers in length. As the ice eventually retreats or sublimates, these channels are left behind as sediment-filled ridges. This discovery on Mars provides compelling evidence for periods of subglacial melting, suggesting a more complex thermal history than a simply frozen past. The very idea that water, even if only fleetingly, might have flowed under these ancient ice sheets is a truly tantalizing prospect. Let us now turn our attention to the so-called sand spiders of Mars. The name itself conjures images of science fiction, but the reality is a geological marvel. No, they won't be devouring future Martian settlers for a snack. They aren't that kind of spider. What we perceive as spiders are actually intricate dendritic patterns etched onto the Martian surface. These landforms, observations have shown, are constantly increasing in size, expanding with each passing Martian year. But what cosmic forces could be causing them to grow? The true architects of these striking patterns are the Martian sand dunes and, more significantly, deposits of dry ice, frozen carbon dioxide that blankets vast swaths of the planet during its colder seasons. As the Martian spring and summer arrive, the air and soil temperatures rise sharply. A portion of this solid carbon dioxide ice warms and sublimates directly into gas, rather than melting into liquid. This process creates a giant bubble of gas accumulating under the surface of the dry ice sheet. The pressure within this trapped gas steadily increases until, eventually, it reaches a critical point and the ice bursts open, ejecting the carbon dioxide gas into the atmosphere. What's crucial here is that this gas eruption also carries with it a massive amount of sand and dust, blasting it onto the surface. This high-pressure air geyser acts like a colossal sandblasting machine, stripping away the surface material. Consequently, the cracks through which the gas escapes grow larger with each seasonal cycle, gradually transforming into the intricate spider-like shapes we now perceive in MRO images. This is Mars, truly a living, breathing world in a geological sense, sculpted by the dance of frozen gases and fine dust, a dynamic theater of the bizarre. It's truly challenging to come to grips with the sheer scale of planetary evolution, to wrap one's mind around the fact that 4 billion years ago, Mars probably resembled Earth more closely than it does today. Its vast expanses, we now surmise, were most likely covered with a shallow ocean, perhaps several hundred meters deep. Certainly not the kilometers of depth we find in Earth's abyssal plains, but a substantial body of liquid water nonetheless. Clearly, there was water. Of this, there is no longer any doubt. Yet, as billions and billions of years passed, Mars rapidly died, becoming a cold, desolate world, losing almost all of its atmosphere to the relentless stripping of the solar wind, a catastrophic transformation that left behind a frozen, silent testament to a once kinder climate. What cosmic forces could orchestrate such a profound planetary demise, transforming a vibrant world into a frozen memory? This question resonates not just for Mars, but for any world in the cosmos. And if Mars offers us a glimpse into a planet's decline, then Pluto, that distant, enigmatic dwarf world, provides a startling counter-narrative, revealing astonishing geological activity in the frozen depths of the outer solar system. For decades, Pluto was simply a cold, tiny, distant speck. Discovered by astronomer Clyde Tombaugh in 1930, it held the title of the 9th planet in order from the Sun for 76 years. It was fittingly named in honor of the Roman god of the underworld, a realm of perpetual darkness and ice. Its orbit, we knew, was an elongated ellipse, unusually inclined at a significant 17 degrees to the flat plane of motion of the other planets. A complete revolution around our Sun takes Pluto a staggering 247 Earth years, and intermittently, for periods of almost 2 decades, it actually drifts closer to the Sun than even Neptune. With a diameter of just 2,374 kilometers, Pluto's mass is almost 6 times less than that of our own moon, and it weighs 480 times less than Earth. Its diameter is only 2/3 that of our natural satellite. Its atmosphere, we understood, was incredibly thin, composed of gases evaporating from surface ice. This, perhaps, was all we knew about Pluto. Then, on a pivotal day, the 14th of July, 2015, everything changed. On that day, the New Horizons space probe, having journeyed for 9 years, 5 months, and 27 days, covering more than 4.5 billion kilometers across the vastness of the solar system, finally flew past Pluto at an astonishing speed of 50,000 kilometers per hour. Thanks to this extraordinary mission, researchers obtained unprecedented high-quality images of Pluto and made a plethora of mind-boggling discoveries. Among other things, they unveiled the existence of cryovolcanoes on its surface, not spewing molten rock, but molten ice and volatile compounds. They postulated the existence of a subsurface ocean of liquid water, a truly astounding thought for a world so far from the Sun. The discoveries continue to be made even to the present day as data from the New Horizons flyby continues to be analyzed. For example, The mission's directors recently managed to completely record and decipher the last portion of research data obtained with the probe's super-powerful space telescope. It turns out that Pluto's subsurface oceans are now considered one of the most intriguing places in the solar system from the standpoint of conditions for life, second perhaps only to Jupiter's moon Europa. Yet how these oceans formed and what dynamic processes might be occurring within them beneath a multi-kilometer shell of ice remains largely unknown. But the findings were a genuine surprise to the mission's directors. No one had imagined distant Pluto would present such an incredibly complex surface. We had pictured a smooth, cold billiard ball. Instead, we perceived a world with a rich, intricate topography, clearly reflecting a turbulent geological history. The new images revealed Pluto to be covered with recently formed mountains, vast plains of ice, dunes sculpted from methane ice, and even icebergs drifting through a sea of nitrogen. Furthermore, the ice crust of this celestial body is riddled with countless cracks, features that strongly suggest traces of recent tectonic activity. These were the first compelling indications of a gigantic subsurface ocean on this dwarf planet. Soon, further evidence emerged, solidifying the presence of liquid water beneath Pluto's icy crust. But how and when did it originate on Pluto? That remains a mystery to this day. However, we now have strong evidence suggesting that Pluto was originally cold. This implies that it grew slowly, accumulating icy material from the outer solar system, and initially there was no ocean. Water in liquid form only appeared on Pluto much later after its core warmed up. This internal heating, scientists believe, was a result of the radioactive decay of short-lived isotopes, particularly aluminium-26, combined with the powerful gravitational interactions and tidal heating exerted by its largest satellite, Charon. In this scenario, the initial melting would lead to the water expanding, and as it refroze closer to the surface, the overall ice crust would have retained telltale signs of surface compression. Why compression specifically? The fact is, when water freezes, it expands. When ice melts back into liquid water, it contracts. If Pluto started cold and gradually warmed, forming a subsurface ocean, that liquid water would occupy less volume than the ice it replaced, leading to a contraction of the overlying ice shell. This contraction would manifest as compressive geological faults on the surface. This is a beautiful example of how planetary geology provides a direct window into the dynamic processes occurring deep within a celestial body. It speaks to a hidden world, a dark ocean, a place where the conditions for life might persist against all odds. Could this seemingly sterile ice dwarf harbor the most tantalizing secrets about the very nature of life in the universe, hiding them beneath layers of primordial ice? It's a question that keeps astronomers awake at night. And what have we learned about Pluto's atmosphere and climate? Pluto's atmosphere is predominantly composed of nitrogen, with minor traces of methane, ethane, ethylene, and other gases. It is extremely thin, with a pressure about 1,000 times less than Earth's atmospheric pressure. Nonetheless, this wispy atmosphere exerts a profound influence, not only on the climate, but also on the geology of the dwarf planet. For example, it facilitates the equalization of temperatures across different regions of Pluto. Moreover, because of the greenhouse effect created by methane, the temperature of the planet's surface is elevated beyond what would otherwise be expected. New data has even demonstrated that some segments of Pluto's surface actually possess snow caps, but these are formed in a completely different way from those on Earth. On Earth, we often perceive clouds converting into snow on mountaintops because temperature decreases with increasing altitude. On Pluto, the opposite is true. The atmosphere becomes hotter as altitude increases, a conceptual inverse. Correspondingly, the physiochemical traits of snow formation and snow caps on Pluto differ dramatically. What we perceive as snow is, in this case, more accurately described as methane ice. Finally, we've come to understand that the change of seasons on Pluto occurs not due to the axial tilt of the planet, as on Earth, but primarily because of its elongated orbit. Over the course of a single revolution around the Sun, which spans roughly 250 Earth years, the amount of heat received by Pluto fluctuates by almost 3 times. As a result, the density of its atmosphere fluctuates significantly. During the long summer, which lasts a little less than half of a Plutonian year, frozen gases like nitrogen and methane evaporate from the surface, enriching the atmosphere. In the frigid winter, they revert to a solid state, settling back onto the surface as fresh ice. This process ensures that gases are carried over the surface of the planet. And over millions of years, these atmospheric currents have sculpted the most amazing forms of relief onto Pluto's icy face. It is a testament to the fact that, even in the most extreme conditions, celestial bodies retain a surprising dynamism. Now, let's cast our gaze back to our own home world and consider a place that might, at first perception, seem alien: Antarctica. It is, undeniably, the least explored continent on our planet, yet it immediately sets several astonishing records. For instance, it is in Antarctica that the strongest winds on Earth persistently blow, powerful katabatic gusts that sweep down from the polar plateau. It was there, at Vostok Station, that the lowest natural temperature ever recorded on Earth was registered, an unimaginable 89 degrees Celsius below zero. And, in a testament to the power of celestial impacts, it is also the location of the largest known impact crater on Earth, buried deep beneath the ice. The Antarctic ice sheet itself is so heavy, so monumentally massive, that the continental landmass beneath it has literally caved in, depressed by almost 500 meters under the sheer weight of millennia of ice and snow. It is true that the surface of this record-breaking continent has been covered with ice and snow for several millions of years. But this has not always been the case. Mariners and explorers of the past often speculated about a warmer Antarctica, a land of mystery hidden beneath its icy shroud. For example, in 1911, expeditions extracted 15 kilograms of geological samples, some of which bore the distinct imprints of fossil leaves from the Permian period. Paleontological and geological data revealed this plant, Glossopteris, grew exclusively in the tropics. And unlike earlier finds collected by a Swedish expedition, these leaves were not merely found near the edge of the Arctic Circle, but almost at the pole itself. 50 years later, in the 1960s, this find became one of the main arguments supporting the revolutionary theory of plate tectonics, especially when traces of similar plants were discovered in Australia, New Zealand, India, Africa, and South America, presupposing the existence of a single southern supercontinent called Gondwana. Nowadays, thanks to advanced technology, research into Antarctica's past is even more productive. Compelling evidence of vast rainforest growth in Antarctica was obtained from a core sample of sediment deposit taken from the seabed near the 90-million-year-old snowy coastline of the Pine Island Glacier. During the initial analysis, the team discovered a fascinating, dense network of roots, permeating the entire layer of soil. This ancient soil was so remarkably well preserved that not only could countless traces of pollen, spores, and the remains of flowering plants be clearly distinguished, but even individual cell structures were perceptible. This new evidence has profoundly reshaped our understanding, demonstrating that the ancient polar landscape wasn't merely comprised of temperate forests, but thriving tropical rainforests. This means that the climate of this present-day ice-cold continent was not just temperate then, but substantially warmer than had previously been assumed. Antarctica, 90 million years ago, was a completely different world. It was alive and flourishing in every sense. In addition to the dense and rich vegetation, a diverse array of animals roamed freely. Herbivores, omnivores, and carnivores thrived. Among them were arboreal forms of animals, by all appearances, something resembling a small marsupial like Marmionero glacialis, akin to a mouse or a possum. Perhaps even small sloths could be encountered clinging to the branches, looking remarkably similar to their modern-day descendants. Among the land animals, the most numerous were representatives of the Sparnotheriodontidae family of mammals, a group of extinct South American ungulates or hoofed mammals that somewhat resembled horses. Judging by the structure of their teeth, they were herbivores, reaching a body mass of up to 400 kilograms. Also on land, one could come across flightless cursorial birds. One was ostrich-like, and another, carnivorous and probably quite dangerous. Along the ancient shores of the Antarctic Peninsula, one might run into king-sized penguins, and in the skies, falcons and caracaras would soar. In the lakes, giant crocodile-like amphibians, such as Antarctosuchus pallidon, waited for prey. Reptiles of all kinds roamed the land. Impressive, massive predators, a small lizard-like insectivore called Prolacerta, and of course, dinosaurs. It was not just a Jurassic Park, but an entire continent teeming with life. The most exotic among them was Cryolophosaurus ellioti, the ice-crested lizard, a formidable predator with a narrow skull measuring 65 centimeters, its huge mouth studded with sharp teeth capable of swallowing a slow-moving person whole, if, of course, there had been any at that time. It lived on the dry land about 200 million years ago, as did Glacialosaurus, a sauropodomorph and distant relative of the famous giant long-necked sauropods. However, Glacialosaurus was much more modest in size, averaging 7.6 meters in length and weighing significantly less, perhaps 4 to 7 tons, which permitted it to rise briefly on 2 legs. Who would have thought that 90 million years ago, near the South Pole, the average air temperature in summer was a balmy 19 degrees Celsius, a tropical green world, rich in flora and fauna? Now, however, these are cold lands, starkly similar to Mars in their frigid desolation. So, what happened? What sort of climatic occurrence could have prompted such global cataclysmic changes? Was it a giant meteorite impact, triggering a worldwide flood or a prolonged global winter? Or perhaps the expansion of the Tasman Sea between Antarctica and Australia, which in previous geological epochs formed a single supercontinent. The widening of the seaway would have altered ocean currents, preventing warm equatorial waters from reaching Antarctica, leading to its gradual freeze. No matter what exact mechanism was at play, the thriving world came to an end. A new era had arrived, the era of the Ice Ages. And as it seems, after millions of years, this dramatic transformation, this swing from lush tropics to frozen wilderness, is a normal part of the long-term climatic evolution for planets of the same type as Earth. What profound, irreversible shifts could transform a verdant paradise into an icy wasteland, and what lessons might Earth learn from such ancient planetary sagas? It's a sobering thought that should drive our continued exploration, for who knows what other cold worlds, hundreds of light years away from us, are hiding under a thick layer of ice, waiting to reveal their own incredible, vanished histories. Our imaginations, spurred by scientific discovery, lead us to contemplate life in the most extreme environments. And speaking of things that defy easy comprehension, that push the very fabric of reality to its limits, let's turn our attention now to the colossal, the almost incomprehensibly massive objects that inhabit the cosmic void, black holes. How massive do black holes truly get? At the moment, we know of sizable examples formed as the cataclysmic result of huge stars collapsing under their own gravity, a process that could theoretically give rise to black holes of truly enormous mass. But stellar mass black holes are mere infants compared to the titans that lurk at the heart of most, if not all, galaxies. We're talking about supermassive black holes, objects with a mass millions or even billions of times greater than our Sun. Take, for instance, Sagittarius A, pronounced A star, located at the very center of our own Milky Way galaxy. Its mass amounts to about 4.5 million solar masses. Of the known black holes, the one with the smallest mass is only 5 times more massive than our star, but 100,000 times more compact. The diameter of some of these black holes is no more than the expanse of a large city, yet the weight of such a munchkin is equivalent to 5,000 suns. The radius of others is comparable to Earth's radius, but their mass is 6 million times greater than that of our planet. Our Earth simply gets lost against that background. Now consider the gargantuan black hole at the center of the Messier 60 galaxy, which has a mass of 4.7 billion suns. The very class of ultramassive black holes begins at around this astonishing mass. The largest of these are made up of even as many as 45 billion suns. Yet, even they can seem like cosmic infants when we consider the truly staggering scales. Currently, the largest known black hole is the Ton 618 quasar, which has a mass of 66 billion times the mass of our Sun. It is located near the North Pole of the galaxy in the constellation Canes Venatici, the hunting dogs. The Ton 618 quasar is believed to possess an accretion disk of incredibly hot gas orbiting the giant black hole at the center of its galaxy. The emission lines in the spectrum of Ton 618 are unusually wide, which tells us that the gas in the accretion disk is moving at very high speeds, about 7,000 kilometers per second. The galaxy itself, in the center of which the quasar is located, is not visible from Earth due to the sheer brightness of the quasar itself. Its absolute stellar magnitude is 140 trillion times greater than that of the Sun. It is precisely because of this overwhelming luminosity that its exact mass has been so difficult to determine. But what of a new challenger, one that bears the name Holmberg 15A? Holmberg 15A is a Type CD supergiant elliptical galaxy located in the Abell 85 galaxy cluster in the constellation Cetus, about 700 million light-years from our Sun. Galaxies of Type CD are a subclass of giant elliptical galaxies of morphological class D. Such galaxies have enormous stellar halos and can be found near the centers of some large galaxy clusters. They are often considered the potentially largest representatives of galaxies in the universe. Holmberg 15A was discovered in 1937 by Erich Holmberg. The galaxy became famous after it was announced that it had the largest of all observed galactic cores, sprawling about 15,000 light-years in expanse. But then, that discovery was initially refuted. Now, however, Holmberg 15A is once again taking the lead. The fact is that the Abell 85 cluster exhibits a velocity dispersion in a dark matter halo of about 750 kilometers per second. This remarkable velocity dispersion can only be explained by the presence of a supermassive black hole with an immense mass of at least 170 billion solar masses. Although the halo of dark matter is not subject to this kind of scaling, the evolution of a black hole within dark matter is directly related to its surrounding baryonic matter. Notably, among known objects, this is one with the heaviest supermassive black holes. This classic case tells us that the main component of the galactic core is a supermassive black hole with a mass of about 40 billion solar masses and a radius of about 790 astronomical units. By comparison, Pluto is located at a distance of about 39.5 astronomical units away from our Sun. However, according to newly analyzed data, the gamma radiation emanating from this object is so extensive that some researchers now estimate Holmberg 15A's mass at 310 billion solar masses. How is it possible for an object to be so unimaginably massive? Let's try to decipher this galactic mystery. It became obvious from observation that the distribution of stellar orbits was shifting more and more towards tangential motion inside the core. However, the displacement is less than in that of other elliptical galaxies with cores. This tells us that at an earlier time there was a merging of galaxies, each containing black holes. Astronomers have now detected that the observed magnitude of tangential anisotropy and the shape of the light profile are remarkably consistent with a formation scenario where Holmberg 15A is the remnant of the merger of two supergiant black holes. And now the masses of black holes and galaxies with cores, including Holmberg 15A, are proportionally scaled inversely with the brightness of the star's central surface and the density of the mass, respectively. That is precisely why the black hole Holmberg 15A has taken its position as one of the largest and hungriest supermassive black holes. The new estimate of its size ranges from 40 to 310 billion solar masses, and its rate of accretion of matter is estimated to be between 8,000 and 45,000 times more massive than the black hole at the center of our Milky Way. If the black hole in our galaxy were to accumulate that much matter, it would have to mercilessly swallow 2/3 of all the stars in the Milky Way. Further research will undoubtedly reveal the full secrets of this extraordinary object. But no matter what, the Holmberg 15, a black hole, is, by current understanding, the heaviest among all that have been discovered thus far. What does it mean for the structure of the universe, and indeed for our understanding of reality, that such incomprehensible titans of gravity exist? It's a question that pushes the very limits of our imagination. Our understanding of planetary systems beyond our own is constantly evolving, challenging our preconceived notions of stability and order. For many years, we largely considered systems like our own, with a single star and planets orbiting in a relatively flat plane, to be the norm. Yet in space, there are far more complex star systems known, with 2 or even, more rarely, 3 stars, all spinning around each other in intricate gravitational ballets. However, a truly groundbreaking discovery provides compelling proof that this is by no means the limit. A group of astronomers was able to detect a system in the universe with 4 stars. Amazingly, all this time, it was hiding a mere 146 light-years from us. Instances of systems consisting of 4 stars are incredibly rare. However, the uniqueness of this particular object, designated HD 98800b, is further enhanced by the fact that it also possesses a protoplanetary disk. Using the Spitzer Space Telescope, astronomers discovered that this disk is composed of 2 distinct belts. The outer belt is separated from the center of the double star by 5.9 astronomical units, almost the same distance separating Jupiter from our Sun. Researchers suspect this belt is composed of comets and asteroids, raw material for distant worlds. The inner belt is located at a distance of 2 astronomical units from the center, roughly where Mars orbits our Sun, and appears to be formed of fine dust. This kind of division in a protoplanetary disk usually occurs during the formation of a planet, as the nascent world sweeps up material in its orbital path. But in this case, this division likely arose for another, more profound reason, under the overwhelming gravitational influence of the neighboring binary system, HD 98800a. How is this possible? The fact is, in most stellar systems, protoplanetary disks are aligned with respect to the main star's equatorial plane. For example, in our own solar system, all the planets and most of the asteroids spin approximately on the same plane with the Sun. But this does not apply to HD 98800. It has a disk of gas and dust that is positioned at a right angle to its central stars. This is the very first system known to us with a perpendicular disk, and such an anomaly promises many more astonishing discoveries. Presumably, if astronomers manage to find other similar older systems, it will be possible to perceive planets spinning in strange orbits at all sorts of angles. In turn, this might lead to the formation of entirely new types of planets, still unknown to science. However, another scenario is also possible. In such chaotic gravitational conditions, planets might simply be unable to form from a protoplanetary disk at all. The very forces that created the perpendicular disk could prevent planetesimals from coalescing into larger worlds. The search, therefore, remains to be continued. In the vastness of space, there are still countless curiosities unknown to mankind. On the other hand, we now understand that planetary formation can, at the very least, begin in these polar circumbinary disks. If the remaining portion of a planet's formation process can occur there, then there may be an entire population of displaced, near-Earth-like planets that we have yet to discover, worlds with such things as utterly peculiar seasonal variations. But although planetary formation may begin, it is profoundly unclear to what extent planets can truly form and remain stable in such a seemingly chaotic system. However, if planets were to exist, the view from one of them in a system like this would be nothing short of utterly amazing. A hypothetical observer would perceive a bright streak of light rising from the horizon and stretching across the entire sky, an incredible celestial arc formed by the combined luminosity of 4 stars. From time to time, individual stars would pass across it, creating a dazzling, ever-changing tableau. Because of this, such a planet would experience an intricate system of seasonal changes that couldn't possibly be compared with Earth's seasons of the year, a cosmic ballet of light and shadow. We have detected an exoplanet in this system, about 1.35 times the size of Earth and 8 times more massive, orbiting the brightest star. In doing so, it receives 5 times more solar radiation from its primary. Researchers calculate that this detected object will make a transit across the face of its star, allowing observers from Earth to perceive a barely perceptible reduction in the light emitted. The incredibly powerful effect of the 4 celestial bodies in this system is literally tearing this planet apart. The extremely high temperatures and high levels of radiation make this place absolutely unsuitable for the emergence of biological life as we know it. If someone does live here, then one can truly feel sorry for them. In the meanwhile, experts hope to understand whether it is possible to replenish the atmosphere of a planet located in extremely close proximity to its star by means of the vapor emitted by the crust of the planet. In a certain sense, the very presence of a planet next to 4 stars could generate some extremely spectacular phenomena, despite the planet being utterly uninhabitable. In addition, the daytime view of the sky on such an exoplanet has to be truly cosmic, a testament to the endless, beautiful permutations of our universe. Our imaginations, spurred by scientific discovery, lead us to contemplate life in the most extreme environments. And speaking of things that defy easy comprehension, that push the very fabric of reality to its limits, let's turn our attention now to the colossal, the almost incomprehensibly massive objects that inhabit the cosmic void, black holes. How massive do black holes truly get? At the moment, we know of sizable examples formed as the cataclysmic result of huge stars collapsing under their own gravity, a process that could theoretically give rise to black holes of truly enormous mass. But stellar mass black holes are mere infants compared to the titans that lurk at the heart of most, if not all, galaxies. We're talking about supermassive black holes, objects with a mass millions or even billions of times greater than our Sun. Take, for instance, Sagittarius A.S. pronounced A star, located at the very center of our own Milky Way galaxy. Its mass amounts to about 4.5 million solar masses. Of the known black holes, the one with the smallest mass is only 5 times more massive than our star, but 100,000 times more compact. The diameter of some of these black holes is no more than the expanse of a large city, yet the weight of such a munchkin is equivalent to 5,000 suns. The radius of others is comparable to Earth's radius, but their mass is 6 million times greater than that of our planet. Our Earth simply gets lost against that background. Now consider the gargantuan black hole at the center of the Messier 60 galaxy, which has a mass of 4.7 billion suns. The very class of ultramassive black holes begins at around this astonishing mass. The largest of these are made up of even as many as 45 billion suns, yet even they can seem like cosmic infants when we consider the truly staggering scales. Currently, the largest known black hole is the Ton 618 quasar, which has a mass of 66 billion times the mass of our Sun. It is located near the north pole of the galaxy in the constellation Cons Venatici, the hunting dogs. The Ton 618 quasar is believed to possess an accretion disk of incredibly hot gas, orbiting the giant black hole at the center of its galaxy. The emission lines in the spectrum of Ton 618 are unusually wide, which tells us that the gas in the accretion disk is moving at very high speeds, about 7,000 kilometers per second. The galaxy itself, in the center of which the quasar is located, is not visible from Earth due to the sheer brightness of the quasar itself. Its absolute stellar magnitude is 140 trillion times greater than that of the Sun. It is precisely because of this overwhelming luminosity that its exact mass has been so difficult to determine. But what of a new challenger, one that bears the name Holmberg 15A? Holmberg 15A is a Type CD supergiant elliptical galaxy located in the Abell 85 galaxy cluster in the constellation Cetus, about 700 million light-years from our Sun. Galaxies of type CD are a subclass of giant elliptical galaxies of morphological class D. Such galaxies have enormous stellar halos and can be found near the centers of some large galaxy clusters. They are often considered the potentially largest representatives of galaxies in the universe. Homburg 15A was discovered in 1937 by Erich Homburg. The galaxy became famous after it was announced that it had the largest of all observed galactic cores, sprawling about 15,000 light-years in expanse. But then, that discovery was initially refuted. Now, however, Homburg 15A is once again taking the lead. The fact is that the Abell 85 cluster exhibits a velocity dispersion in a dark matter halo of about 750 kilometers per second. This remarkable velocity dispersion can only be explained by the presence of a supermassive black hole with an immense mass of at least 170 billion solar masses. Although the halo of dark matter is not subject to this kind of scaling, the evolution of a black hole within dark matter is directly related to its surrounding baryonic matter. Notably, among known objects, this is one with the heaviest supermassive black holes. This classic case tells us that the main component of the galactic core is a supermassive black hole with a mass of about 40 billion solar masses and a radius of about 790 astronomical units. By comparison, Pluto is located at a distance of about 39.5 astronomical units away from our Sun. However, according to newly analyzed data, the gamma radiation emanating from this object is so extensive that some researchers now estimate Homburg 15A's mass at 310 billion solar masses. How is it possible for an object to be so unimaginably massive? Let's try to decipher this galactic mystery. It became obvious from observation that the distribution of stellar orbits was shifting more and more towards tangential motion inside the core. However, the displacement is less than in that of other elliptical galaxies with cores. This tells us that at an earlier time, there was a merging of galaxies, each containing black holes. Astronomers have now detected that the observed magnitude of tangential anisotropy and the shape of the light profile are remarkably consistent with a formation scenario where Homburg 15A is the remnant of the merger of two supergiant black holes. And now, the masses of black holes in galaxies with cores, including Homburg 15A, are proportionally scaled inversely with the brightness of the star's central surface and the density of the mass, respectively. That is precisely why the black hole Homburg 15A has taken its position as one of the largest and hungriest supermassive black holes. The new estimate of its size ranges from 40 to 310 billion solar masses, and its rate of accretion of matter is estimated to be between 8,000 and 45,000 times more massive than the black hole at the center of our Milky Way. If the black hole in our galaxy were to accumulate that much matter, it would have to mercilessly swallow 2/3 of all the stars in the Milky Way. Further research will undoubtedly reveal the full secrets of this extraordinary object. But no matter what, the Homburg 15. A black hole is, by current understanding, the heaviest among all that have been discovered thus far. What does it mean for the structure of the universe, and indeed for our understanding of reality, that such incomprehensible titans of gravity exist? It's a question that pushes the very limits of our imagination. Our imaginations, spurred by scientific discovery, also allow us to conceive of life in forms utterly alien to our terrestrial experience. Consider the fictional universe of Dune, for instance, conceived by the writer Frank Herbert, and depicted by him in the Chronicles of Dune series of books. This universe was later recreated in a number of film adaptations. While one could discuss the Dune universe for hours, let's focus on its most awesome creation, both in size and in fame, the sandworm. It may be considered the signature element of the Herbert saga. The worm, infamously known as Shai-Hulud by the inhabitants of the desert planet Arrakis, is not merely a giant creature. It has become a philosophical symbol, etched into popular consciousness by illustrations such as John Schoenherr's iconic 1965 depiction for the first magazine publication of Dune, showing the worm's mouth consisting of 3 parts. Though it is not explicitly specified in the novel, this visual interpretation of the creature's jaws was later adopted by designers for David Lynch's 1984 screen adaptation, solidifying the image in our collective imagination. As for obvious reasons, we won't be perceiving large sandworms furrowing through the Sahara or the Atacama Desert of Chile on our planet, and you can be confident it's for the best. But nobody truly knows the chances of finding a creature in deep space that resembles such a creation of science fiction. So, let's take this topic into scientific consideration and ask the fundamental question: could the worm Shai-Hulud exist in reality? To begin with, let's clarify what this giant crawling creature is. According to Herbert's description, the sandworm is composed of 100 to 400 individual segments enclosed in a thick, silvery gray, leathery shell. Each segment possesses its own primitive nervous system, making it almost impossible to kill the worm. Even if one segment is destroyed, the other parts will, in theory, take over its functions. Sandworms are enormous, with average individuals reaching 400 meters in length and the largest exceeding 2 kilometers. The mouth of a large worm measures 80 meters in diameter. Just imagine a huge maw the size of a 26-story building surrounded by a multitude of sharp teeth. Yes, indeed, Shai-Hulud is every fisherman's worst nightmare. But the most distinctive aspect is that the worm from Herbert's universe is not a member of the animal kingdom as we know it, but a silicon-based life form that fears water. All living creatures we know on Earth have common basic features. They grow, reproduce, respond to environmental stimuli, are able to adapt, and sometimes even change. In addition, they share a common basis for all biochemistry. They are made of long chains of carbon molecules that use water for metabolism and energy. But it is certainly possible that a non-carbon-based life form exists somewhere, and that such a life form would be very different from what we are used to experiencing. The ability of carbon to form long chains makes it an ideal base for the building of sufficiently complex molecules that a body requires to carry out vital functions. Yes, carbon is great for forming complex molecules, but it's not the only element in nature that can do it. There is also silicon, which sits directly under carbon on the periodic table of elements. This tells us that, theoretically, such a life form is possible. In addition, if a sandworm generates oxygen, then the question arises, what does it use as a source of energy? The answer to this is facilitated by the example of one extraordinary microorganism called the chemotrophic bacterium. This bacterium uses chemicals to sustain itself, usually hydrogen sulfide, to provide itself with the energy needed to synthesize carbohydrates from carbon dioxide and release oxygen. Since hydrogen sulfide is often emitted from underground volcanic craters, it is the most likely source of subterranean energy in Dune's universe. And because sandworms live deep in the bowels of the planet, far from the sun and any processes of photosynthesis, they would have to use chemicals, most likely hydrogen sulfide, to provide essential energy. As far as the movement of the giant worm in the desert is concerned, that is an extremely interesting question. This is because the truth is that the existence of such massive sandworms on Earth isn't possible. Despite their fearsome appearance, ordinary sand on Earth would simply crush the poor creature due to the overwhelming pressure and friction. So, we would have to move to another planet where 2 important conditions would be met. First of all, low gravity is absolutely necessary for the movement of such a massive organism under the surface. The less gravity, the better. A planet like Mars with a magnetic field and lower gravity is a good candidate. Secondly, clay is best suited for the movement of the sandworm, providing lubrication and reducing friction, but on Arrakis the events take place in a desert. To some measure, part of the sand is a possible habitat if we are talking about large grains that make it easier to breathe and to dig a little deeper. Quartz chips would work just fine. Now, with these conditions, Shai Hulud is theoretically more comfortable and perhaps even smiling, but that's better left unimagined. Could life, under the right extreme planetary conditions, truly evolve to such monstrous, silicon-based forms, thriving on volcanic gases beneath arid plains? It's a thought that stretches the boundaries of our biological expectations. Finally, let us consider Europa, that enigmatic moon of Jupiter, a true beacon in our quest for life beyond Earth. Europa is Jupiter's biggest moon, not in size but in its potential. It harbors a huge ocean beneath its surface, a colossal body of liquid water trapped under a vast layer of ice. The moon's water doesn't freeze solid even in the frigid Jovian system because of Europa's hot core, which is continually heated by the immense gravitational flexing caused by Jupiter's powerful tidal forces. This fascinating truth first became known in the early 2000s, thanks to the Galileo probe, which detected the telltale magnetic signatures of an electrically conductive liquid beneath Europa's surface. Galileo also revealed Europa's surface to be exceptionally smooth, one of the flattest in the entire solar system, a testament to its dynamic icy crust. It might seem that this is where our knowledge ends, but this is far from true. Over the past 20 years, and especially recently, we have gleaned a wealth of exciting details about this distant satellite. Europa, even now, is far from a dead object. Scientists have detected enormous geysers or plumes which eject vast amounts of water vapor into its tenuous atmosphere. It's a known principle that water molecules emit specific frequencies of infrared light as they interact with solar radiation. This distinct signal was captured by scientists at the Keck Observatory, utilizing a spectrograph specifically designed to measure the chemical composition of planetary atmospheres. The observations spanned 17 nights, and during that period, the scientists detected one weak yet unequivocally clear water stream signal. Analysis of the data revealed that these water molecules were being ejected from Europa on the side visible from Jupiter, a crucial piece of evidence. According to the researchers' calculations, the blowout was so powerful, containing so much water, that it could fill an Olympic-sized swimming pool in just several minutes. Water was entering the atmosphere at a rate of about 2,360 liters per second. If any dwellers of Europa had been caught in that stream, that would have certainly been their last terrifying attraction. The good news, if you could call it that, is that any inhabitants who managed not to be blown into outer space would be very easy to perceive, as Europa's surface is one of the flattest in the solar system. The tallest formations one might encounter are merely several hundred meters high. If we examine Europa's surface images more closely, we perceive clear signs of endogenous geological activity. Intricate networks of lines, enigmatic lenticulae, strange bumps and pits, and the chaotic terrain known as chaos regions. We also perceive areas dominated by lines and stripes, usually doubled ridges, as well as relatively few impact craters. Their number is small, only 40 named craters larger than 5 kilometers in diameter, which strongly suggests that the surface is relatively young, perhaps between 20 and 180 million years old. So, Europa clearly possesses high geological activity. Spectral analysis of the dark lines and spots on its surface reveals the presence of various salts, magnesium sulfate in particular. The reddish hue of some features allows us to infer the presence of iron and sulfur compounds as well. Apparently, these chemicals are contained within Europa's vast ocean and are ejected to the surface through deep clefts, where they then freeze. In addition, traces of hydrogen peroxide and strong acids were found. For instance, there is a high chance that Europa's surface contains sulfuric acid hydrate. Let's imagine for a moment attempting to land on that intriguing object. As it turns out, it's not that easy. The challenge is that Jupiter's moon Europa is surrounded by a vast region of sharp ice needles, structures known as penitentes or nieves penitentes. These stretch along the entire equatorial region and pose an extremely dangerous hazard for any space probes attempting to land. These ice needles on Europa can reach up to 15 meters in height. Even at such imposing dimensions, these structures cannot yet be clearly perceived on the images of Europa available to us, highlighting the resolution limitations we still face. A few careful maneuvers, and we've hypothetically landed, having managed not to damage our spacecraft on these gigantic icicles. The incredible view of Europa now opens to our eyes. Its surface is unbelievably cold compared to Earth's. The temperature here hovers between 150 and 190 degrees Celsius below zero. But that is not the main thing to worry about here. The radiation level on Europa is incredibly high. The satellite's orbit passes directly through the powerful radiation belts of Jupiter. The daily dose of radiation here is nearly 1,000,000 times greater than on Earth. This dose is enough to cause severe radiation sickness within a single day. But no worries, we have, we hope, a proper radiation protection shield on our hypothetical lander. Well, with this in mind, we dispatch a tunnel robot, powered by a nuclear reactor, into the deep ice of Europa. It is designed to drill through the ice, collecting ice and water samples and sending information back to the surface via a fiber optic cable. Surprisingly, Europa, we suspect, possesses not just one ocean, but potentially several layers of ocean, separated by different types of ice, formed at varying depths and under different pressures. It is likely that in each of these layers, different life forms might be found, species that have adapted to the particular conditions of each ocean stratum. Such possibilities push the boundaries of what we conceive as life. However, if these life forms turned out to be truly unlike anything we have ever experienced on Earth, it might be incredibly difficult for us to even recognize them as life. And besides, we might not find life there at all. But these thoughts, this inherent uncertainty, would never diminish our curiosity, would they? As you can sense, in our explorations and even our imaginings of the cosmos, we often have to disregard some things and conceptually violate a lot of others, pushing the boundaries of our understanding and technology. Interstellar journeys and the discovery of truly alien life are still, for us, very much a fantasy. But what kind of fantasy, what grand dream, doesn't, after a while, gradually transform into reality? It is the enduring promise of science, the ceaseless human drive to peer beyond the familiar, that keeps us looking, keeps us probing, keeps us dreaming of the wonders that await beyond our current horizon.